Let's repeat the previous experiment by using a ferrite ring. There's a ferrite ring, pretty blue colour. It would be even pretty if it was in pink. That is a particularly foul colour, but it's what came. This one is 10, 20, 30, about 38 millimetres, and the hole is about 20 millimetres, 21 millimetres, and the dimension that way is about 11 millimetres. That's not even focusing, is it? Anyway, for some reason the meter now says 3.1 on the same piece of wire, so I think there's something a bit wonky about the leads, but as long as we don't disturb them too much, we should be okay. So let's start by passing it through once. Remember, it was 3.0. What is it going to be now? Oh, passing it through a big ring makes virtually no difference. Unlike the little ring, because we don't know the mix of this ferrite, do we? Let's pass it through again. So we'll now create a turn quite tight on the thing. And it's gone up to 3.4. Still not very much. Okay, let's give it another turn. I wonder if this ferrite is any good. It's the first time I've played with it. Remember 3.4? 3.9. Still disappointing. And we'll pass it through again. So that's now 3.5 turns. Sorry about keep banging the tripod. 4.7 microhenries for 3.5 turns. Four and a half turns gives us 5.5 microhenries. Right, another turn. 6.8 microhenries. .1 microhenries for 1, 2, 3, 4, 5, 6.5 turns. .7. Can't remember what that was before. Anyway, 9.6. Freeze that and we'll see how much going up an extra turn adds. Is it going up by the same amount for each turn? 9.6 to 11.6. Oh, it's gone up 2 microhenries for an extra turn. Now we're starting to get somewhere. .6 to 13.4, just under 2 microhenries. 13.3, What's it going to be? 15.2? Oh, 15.4. So it's gone up another 2. Probably these tightness of these windings makes a difference. So there's a bit of experimental error. If we were to plot these on a graph, we might see what's going on. $15.4, let's have a guess, 17.4? No, 17.9. I've lost track of how many turns I've got to now. I can put more turns on this coil because it's less distance for each turn. 19.9, so that's gone up 2 microhenries. So we'll just go up another 2 microhenries. I bet you're asleep now. Yeah, no, more than 2 microhenries. That's gone up about 2.7, hasn't it? I hope you like watching this as much as I like making it. If you do, give me a like. Nobody's given me a like yet. 22.7, 25.4. I think I'm going to draw a graph, and it might make it a bit clear what's going on. 25.4, 28.5. So that's gone up nearly 3 for the last turn. Now, how many turns have we got on that for the sake of posterity? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I don't know. And I just realised all that was out of shot. There he was, 15 turns on there. Here's the tabulated results for the blue-green ferrite ring. As before, it was with no passes through the ring. The inductance was 3 microhenries this time. So that's the figure that we can subtract from all these other figures. So we went up to 16 turns, and it gradually increased, very slowly at first and then a lot quicker at the end. When we subtract the 3, we get these figures in microhenries. Now the interesting thing is, for 1 pass you got 0.1 microhenries. For 2 passes, twice the number of turns, we got 0.4 microhenries, which is the square of 2. 2 2s are 4. 3 3s are 9. 4 4s are 16. Do you see the pattern? 5 5s are 25. 6 6s are 36. 7 7s are 49. 8 8s are 64. I'm sure you all know your tables. 9 9s are 81, so that one's a bit out. 10 10s are 100. 11 11s are 122. 12 12s are 144. 13 13s 169. 14 14s 196. 15 15s 225. 16 16s 256. You can see how closely those agree to the square of the turns. You know, these aren't turns, these are passes through the core. So 1 whole turn is 2 passes. So if we calculate the number of microhenries per square pass, or passes squared. So I've used P to denote passes. And it comes out really, really close to 0.1. Or, as they tend to do it in the books, nanohenries per square pass. So that would be 106 nanohenries. As you see, at the higher turns, it drops just below 1. But to all intents and purposes, it's near enough 100 nanohenry per squared turn for this size and composition. On a different ring of the same composition, it will be a different AL value. Now I stuck those values into the ferrite calculator, and it gave the UI, which is the initial permeability, as 79. Which is quite low. Remember, on the previous one, we got an initial permeability of 270 something. After filming that, I began to wonder if this core was a fake. After all, it came from China via eBay. And, well, we know what eBay is like, and stuff from China. Maybe it was just painted steel. Anyway, I scraped off some of the paint on each side so that I could test the resistance, and it turned out to be low. Not 0, but low. I think the best I could get it down to was about 130 ohms. But it's not a dead short circuit, so it isn't steel. You know, that's one thing to say, it's not steel. Anyway, it can't be nickel zinc, because if it was nickel zinc it would be high resistance. And it can't be manganese zinc. Excuse me. It can't be manganese zinc because that's got much higher permeability. But it can't be steel because that would have no resistance. So what is it? And then the penny dropped. It isn't ferrite at all. It's powdered iron. It was sold as ferrite, but it's powdered iron. This probably explains why it's painted with a good thick layer of paint. And get that out of the way. And it's got very, very rounded edges. Lovely rounded edges. Unlike some ferrites, which are a bit sharp on the edges. And I reckon that's because it's a conductive material, and if you're winding turns of copper wire around there, it would, if it wasn't painted, it would cut through. If it wasn't rounded and painted, it would cut through the windings, short them out. Isn't the lighting bad in here today? Colour code to these things, but nobody seems to agree on what it is. And if you search, the colour code, you don't come up with the answer. The measurements suggest it's a T150 core. Now, toroids, powdered iron toroids, are measured in inches for some reason. And if it's 1.5 inches across, it's a T150. Say if it was a 1.3 inches across, it'd be a T130. So we know it's a T150 core. Okay, so I started looking for T150 cores with a permeability around 75, because we know that from the previous measurement. Now there's only two mixes of powdered iron that give us a permeability around 75. And one is the type 26 and the other is the mix 52. And only the 52 comes in the T150 size. The 26 is T157. So I, assume that this is a T150-52. And when I looked it up on the web, the colour code matched. So this is definitely a T150-52. And it's not a fake. Yay! Anyway, I could have saved myself all that bother because I went to my eBay purchases, looked it up, and there it was in the instruction, in the specifications, T150-52. Now, I know you can't always trust what the Chinese say things are, but in this case it seems to be true. And why didn't I look there in the first place? I've gone through all this rigmarole, measuring it, measuring the inductance per unit, per turns, and all the rest of it, just to arrive at what I should have known in the first place. But then again, it's all self-training, it's all learning. I didn't know anything about toroids before I started all this. I've used them before, but I've never really thought much about them. I just thought they were all the same. Anyway, so having bought these things, what am I going to do with them? The permeability is low. It's only about a third of the ferrite that I was using. Those ferrite clip-ons have got a permeability around about 250, and this one's only got a permeability of 75 or 79 it was measured at, but I may have made a few slight errors in measuring the sizes of it. So I think it's, we can assume it's got a permeability of 75, so it's just under a third of the permeability of the ferrite materials. And when you look at it, it says maximum frequency about 590 kilohertz, so it's not going to be much good for balance or RF transformers or anything like that. But the thing is that because the maximum frequency is 590 kilohertz, above that it gets very, very lossy, and that's what you want for suppression. You want a lossy material. It's not all about the inductance, it's about how much can you dissipate, how much RF can you get rid of. If you clip a ferrite onto a cable, you get just under a microhenry if you pass it through once. But you can do this with the rings. You can pass them through many times. Now I haven't done a very nice job of that. That's just a quick. I don't intend to leave that on there. But you would, wind it sort of like that and clamp these ends with a cable tie on say a DC power cord. Or you could do that on an Ethernet cable. You can get about five turns, 5 passes through the core on an Ethernet cable before it gets too big for this end to go through. Now, if you just put a clip on a ferrite core, one of these jobbies, it can only go through once. If you get a very big one, you might get it to go through twice. But the problem is that doesn't have much inductance. And at 30 megahertz, it's only a few tens of ohms. Whereas if you can stick it through 5 times, you've got 2.5 microhenries of inductance. And at 30 megahertz, I can't remember the figure, but it's quite significant. Interference from Ethernet cables, that's actually better than using a clamp. And you might stick it on the power supply, on the cable coming out of a power supply. There's the other thing, you could use a big clamp and stick it round more than once, but because I wondered, okay, I now bought these rings, what am I going to use them for? But there you are, that's what you'd use them for. So, thank you for joining me on my voyage of discovery into the strange world of ferrite rings that aren't actually ferrite. I'm sure I'll have a lot more to say about these in the future. If you liked it, give me a like if you want to. I'm not forcing anybody to do anything. But it's quite lonely here, without any likes. It's getting quite dreary, so if you give me a like, at least I'll know that somebody out there is watching it. Or give me a dislike if you like. If you don't like the video, if you hate the sound of my voice, or I'm far too slow for you. Either way, just give me some feedback. Again, if you want to. Bye.